We have a rectangular loop made up of a C-shaped wire and a vertical movable bar as shown in the picture. The vertical bar has length capital L and it has mass m. So initially the bar is given an initial speed v0 pointing to the right, and it keeps moving until it comes to a stop. The first question is, what is the magnitude of the magnetic force acting on the bar as it's moving with speed v? Let's apply the formula for the magnetic force acting on a current carrying wire. In this case, the wire is the bar. F sub b is equal to I times L cross b. I is the current in the bar. L is the vector with magnitude equal to the length of the bar and direction pointing in the direction of the current in the bar. And B is the magnetic field vector. Now, because vector L is pointing either up or down, we don't know the direction of the induced current right now, but it's along the bar, so it's vertical, either up or down. And the magnetic field vector is into the page. L and B are perpendicular to one another. So the angle between vector L and vector B is 90 degrees. Therefore, the magnitude of L cross B is simply equal to L times B. The magnitude of vector L times the magnitude of vector B. So then this cross product formula, if we're only interested in the magnitude of the magnetic force, it reduces to I times L times B. So this will give us the magnitude of the force acting on the bar, which is what we're looking for. Now, do we know everything we need? Do we know the magnetic field magnitude? Yes, so that's given. Capital L is given, that's the length of the bar. Now, one thing that is not given is the current in the bar, and that is the induced current as the bar is moving to the right, because the flux through the rectangular loop increases since the area increases as the bar is moving to the right. So let's go ahead and calculate the induced current. To calculate the induced current, first we need to calculate the induced EMF, and for that we are going to apply Faraday's law. In this problem, the orientation of the bar is perpendicular to the magnetic field vector, and the velocity of the bar is also perpendicular to the magnetic field vector. Plus the velocity vector is perpendicular to the orientation of the bar as well. So all these three directions are perpendicular to one another. So we can use the motional EMF formula, V times B times L, for the induced EMF in the bar. So in our rectangular loop, the induced EMF is V times B times capital L. Also, in the problem, the resistance of the vertical bar is given, that's capital R. So we can use Ohm's law to substitute I times R for the induced EMF. I being the current in the bar or in the rectangular loop. So we get I times R equals V times B times L. We divide both sides by R, we get I equals VBL divided by R. That's the induced current in the loop, and therefore the induced current in the bar as it's moving to the right at speed V. Finally, we substitute this expression for I back in the formula that we came up with for the magnetic force F sub B right here, and simplify. We get F sub B equals V times B squared times L squared divided by R. The next question is, how far does the bar travel given that it started with an initial speed v0? So this suggests that the bar eventually comes to a stop, meaning there's an acceleration in the direction opposite the direction of its velocity. That will be pointing to the left. Now, is that true? If we have acceleration vector pointing to the left, that means the magnetic force acting on the bar is pointing to the left. Let's first verify that. Let's first determine the direction of the induced current in the bar. Now, the magnetic flux through the rectangular loop, which is this loop right here, of course, the magnetic flux through this loop is into the page. As the bar is moving to the right, the magnetic flux is increasing into the page. The response of the loop will be to oppose to that and to create a magnetic field in the opposite direction, which is out of the page. If the loop is creating an induced magnetic field out of the page, what must be the direction of the induced current in the loop? Let's use the right-hand rule to determine that. Align your right thumb in the direction of the induced magnetic field, which is out of the page. The curling direction of your fingers will be counterclockwise. So this is the direction of the induced current. Now we can determine the direction of the magnetic force acting on the bar. Remember, the formula for magnetic force is I times L cross B, L being the vector with direction pointing in the same direction as the current. So the current is pointing up in the bar, that is the same direction as vector L. L is pointing up, B is pointing into the page. What is the direction of L cross B? Align your right hand in the direction of L, which is pointing up. Curl your fingers in the direction of B, which is into the page. Your thumb is pointing in the direction of L cross B, which is the direction of the magnetic force. And that is pointing towards left. So the magnetic force is indeed pointing towards left. This is F sub B. Physically, what does that mean? That means we give the bar an initial velocity v0 towards right, and as the bar is moving to the right, there's a magnetic field acting on it pointing left. And that's the net force acting on the bar. The direction of the net force points to the left. That means the acceleration of the bar will be pointing to the left. Because velocity and acceleration vectors point in opposite directions, the bar will slow down and come to a stop eventually. So from the net force, which is basically the magnetic force, we can calculate the acceleration of the bar applying Newton's second law. Once we know the acceleration, we can use the kinematics connections between acceleration, velocity, and position to find the displacement of the bar. Here we have applied Newton's second law on the bar. Net force in the x direction is equal to mass times acceleration in the x direction. What forces do we have in the x direction? We only have the magnetic force pointing left, hence I have the negative sign for F sub B. So we get negative F sub B equals mass times acceleration, ma. Because this is a one-dimensional problem, I am going to drop the index x, so I'll just use a for acceleration instead of a sub x. So we have negative F sub B equals ma. We're looking for the acceleration. We rearrange our equation to isolate the acceleration and then substitute the expression we found for the magnetic force from the previous part of the problem. Therefore, acceleration is equal to negative vb squared L squared divided by r times m. So we'd like to find the displacement of the bar, so we need to go from acceleration to position, right? To go from acceleration to position, we need to take the integral of acceleration with respect to time twice. If you integrate acceleration with respect to time once, you get velocity. If you integrate once again with respect to time, you get position. So, and from the change of position, you can find the displacement in principle. Now, here we have a problem. Why? Because the acceleration, the expression that we got for acceleration does not explicitly depend on time. It depends on velocity. Now, we know that velocity changes with time, so it still has a time dependence, but it's not explicitly given. Now, can we still find the acceleration? Yes. In the next step, let's substitute dv dt for acceleration and then use the separation of variables to integrate both sides of the equation. That way we will find an expression for v, the velocity, as a function of time. Here we substitute dv over dt for acceleration and then we separate our variables. I have dv on one side, dt on the other side, and I have v on the same side as dv because I'm preparing to take the integral. Now I have replaced my variables with the primed versions. Instead of t, I have t prime here. Instead of v, I use v prime. Why is that? Because when I take the integral, I'm going to use v and t, the variables v and t, as the upper bounds of my integral. That's why I'm using the primes to distinguish between my integration variable and the upper bound of my variable. Now on the left hand side I'm taking the integral of 1 over v prime. That gives me a natural log. And on the right hand side I'm just integrating a constant. That gives me that constant times t. And in the next step, let's isolate v and have an expression of v velocity as a function of time. Next, I use the property of natural log to simplify the left hand side of my equation. ln v minus ln v0 is equal to ln of the fraction v divided by v0. And then in the next line, I take the exponential of both sides to get rid of ln, because I'm trying to isolate v, which is on the left hand side. So then I get v divided by v0 equal to exponential of this term in parentheses that depends on time. And note that this is a negative exponential. And then finally I multiply both sides by v0 to isolate v. Now I have an expression for v, the velocity, in terms of time. We can see that velocity decreases exponentially with time. At t equals 0, the exponential term becomes equal to 1, so velocity is equal to v0 as expected. And as t goes to infinity, the exponential goes to 0, meaning v goes to 0, so the bar stops eventually. Finally, let's go from velocity to displacement. To calculate the displacement, we simply take the integral of velocity over time, and time goes from 0 to infinity. Why is that? At the beginning, t equals 0. Now at the end, why do we have t equals infinity? Well, we want to know the displacement of the bar until it stops, right? When does the bar stop? When v equals 0, and that requires that t goes to infinity. That's why for the upper bound here we have infinity. We simply take the integral. This is the integral of an exponential. The integral of an exponential is itself. We just need to multiply by the reciprocal of the constant here, which we have right here, and we also have a factor of v0, which I included here. So this is our constant, and we're evaluating the exponential from 0 to infinity. So let's see the value. Let's see what we get from here. This is exponential of negative infinity, which is 0, minus exponential of 0, which is 1. So from the term in the square brackets, we get 0 minus 1, that's a factor of negative 1, and it cancels the overall negative sign that we have here. After canceling the negative sign, this is what we get for the displacement of the bar. It's equal to v0 rm divided by b squared times l squared.